Let's take a look at some astronomy. Today I want to talk about basically just an image. There isn't really much science to talk about here. Well, I mean, there's a lot of science to talk about here, but I guess more so what I mean is there isn't really a paper to talk about here. It's just, here's a picture, I'm going to talk about the picture. It's actually a few pictures. But these are the newest images out of JWST. So the James Webb Space Telescope, I talk about it all the fucking time. I love this instrument. It has given us some of the most beautiful images I've ever seen in my life, and that's to be expected given how good it is at what it does. So we're going to take a look at what this article calls an exploded star. At this point, I think you guys have watched enough of me, those of you who have been around, to probably be able to tell me what the actual word for an exploded star is. I think everyone here probably knows it's called a supernova. We're taking a look at what's called a supernova remnant. It is the leftover from a supernova, so when this star has its massive explosion, it sends out a bunch of material, it ejects it in a roughly spherical shape, plus or minus all the perturbations, and we can look at that remnant through a different type, or through some different filters, specifically JWST being an infrared instrument, which is looking at the near-infrared and the mid-infrared. But you can look at these things and see them bright in basically any region of the spectrum. They're highly energetic events, so you can have everything from the afterglow of the gas being heated, which comes out in infrared, the shock wave, which comes out in infrared, some of the other types of radiation we'll talk about that come out all over the spectrum, obviously the visible flash of light. All of this stuff is stuff we can capture. We're specifically looking at the infrared, the near-infrared, and the mid-infrared, which I should actually pull up. I don't think I've ever done this before. So, this is the electromagnetic spectrum. The visible light that we see is light in this tiny little section, but light can exist in all different wavelengths. So we can have light that has wavelengths of up to a meter or bigger, or down to a nanometer and smaller, even all the way down to like the size of atoms. Light exists across the entire spectrum. The sections that we can see are about 400 to 700 nanometers. What JWST is looking at is it's looking in the infrared part of the spectrum, which goes anywhere from about a micron to around a centimeter. This calls that radio waves, even though there's another section in here called microwaves. In this region is where JWST is looking. Specifically, the images that we're looking at are what are in the near infrared, which is near the visible spectrum, and the mid-infrared, which is in the middle of the infrared part of the spectrum. So we're looking kind of around this area. So let's take a look at these images and actually, well, first of all, just look at them because they're gorgeous, and then we'll talk about them a little bit. So here's what they look like. Over here is in the near infrared. It says it right here. This is the near cam. And you get all of these beautiful colors, all of these pinks and purples. Now, of course, being in the infrared, these are not real colors. These are assigned colors, as a lot of astronomy images are. And all of these different colors are referencing some different portion of that portion of the spectrum. So if we're looking at, I don't know, say 1 micron to 10 microns, we might call 1 to 2 microns blue, 2 to 5 or 2 to 3 microns, 2 to 4 microns green, whatever, it doesn't matter. You just label them and you paint the sky basically with those colors. And then if we look over here at the MIRI image, this is the mid-infrared image, we see it looks similar, but we have some different structure here. So if we kind of look at them side by side, we can see this kind of like smoky spherical outside, this spherical shell. Of course, it's not perfectly spherical. You've got some bumps out here and some structure on the inside, but you've got a roughly spherical shell that looks kind of like, almost like gun smoke. The most obvious things in the mid-infrared image are these big orange puffs and this green stuff in the middle, as well as all of this that we can see in both of the images that form this kind of like broken halo. Almost looks like something out of Elden Ring, actually. So we're going to talk about some of the actual individual structures in these images. We're going to start over here on the near cam image, because this has a lot of stuff that we can talk about very easily, whereas the stuff in the mid-infrared has some question marks around it. Let's actually take a look at this image right here. In fact, here's a better version of it. And this looks at a few particular points of interest throughout this image. First of all, I'm going to talk about this larger structure. You're probably wondering what sort of this gun smoke looking effect is. This is actually the shockwave being caused by that initial explosion. So this is the extent of that shockwave moving through the interstellar medium. When this explosion happens, it ejects a ton of material, which is what all of the actual colored stuff is, and it also ejects a bunch of small charged particles, which end up forming this sort of gun smoke cloud. And the reason they do that is because as they're zooming through space at an appreciable percent of the speed of light, somewhere 10% or so or higher, these particles are actually interacting with the magnetic fields, and they get to make some really crazy stuff. Charged particles do really interesting stuff in a magnetic field. You're gonna have to take this for granted because it's just how it works, but I pulled up a little image for you. Turns out that as a charged particle moves through a magnetic field, in this case these little circles with dots in them mean that the magnetic field is pointing into the page, so it's pointing into the computer monitor, as a charged particle moves through that space, it gets accelerated perpendicular to its motion. The reasons for this are complicated. They are basically just something that falls out of Maxwell's equations. And if we have a charged particle that's shot out from the center of this initial explosion, it's possible that it could come out with some amount of tilt compared to that initial point source. So if we have the initial point source here, and it gets shot out in this direction, but it might be tilted a little bit, we could have magnetic field lines that are coming out radially, or they could be doing a weird thing, and it could basically move in some direction that isn't directly aligned with the magnetic field. So even though it is moving partially with the magnetic field, it's moving partially perpendicular to it, which means that we get sort of a helix pattern as it escapes into interstellar space. If we have a charged particle that's shot out from the center and it goes through some amount of magnetic field lines that aren't directly parallel to that movement of that particle, you get what's called synchrotron radiation. And it looks like this. I'm not going to go into the details of why this works, but the important thing to note is that when a charged particle is accelerated, it will release radiation. We've talked about this in the past a little bit. In the case of a particle that's moving with a huge velocity, it can cause these little light cones. They kind of look like light teardrops in this case, but they can cause these little light cones that shoot out as this particle swings past. Now in this diagram, it's showing it in just these positions, but as it says up here, it's emitted throughout the whole trajectory. And depending on the speed of this particle and the strength of the magnetic field, we can get tons of different wavelengths coming out from this process. Fun fact, this process was actually first found in a machine called a synchrotron, which is effectively a big magnet that makes a circular magnetic field, and they saw this light coming off of the charged particles moving in that field, and they dubbed it synchrotron radiation because it's, well, radiation that occurs when you put a charged particle in a synchrotron. As this thing goes around, it emits light, and that light can be all throughout the spectrum, which means that we get this faint white glow as these particles escape. So that's what this white gas looking stuff. It's not really gas. I mean, it kind of is gas. It's charged particles, but it's what this white stuff is, partially synchrotron radiation from these charged particles moving out and spinning around and releasing light as they do so. We'll go back and we'll talk about why portions of this had sort of that like orange section on the mid-infrared. We'll talk about that in a little bit. But for now, let's look at this number 2 right here, which has a zoomed in pane over here. I unfortunately couldn't find the high res images, so we're gonna have to work with these medium res ones. They're still pretty gorgeous though. If we look at 2, we can see the reason that they kind of zoomed in on this. There's these little circles. They might be hard to see. Actually, the stream's picking it up pretty well. And what are these? Well, these little circles, you can kind of think of them like bullet holes, where when these extremely high energy particles got shot out from the supernova, they passed through the interstellar gas or the gas surrounding the star initially and just shot right through them, basically like a bullet going through smoke. So as it pierces a hole through it, basically makes a little shockwave, and that shockwave is what we're seeing here. That's what these little circles are. These are big clumps of gas or plasma being shot out at such high speed that they make these little ripples in the interstellar gas, which is fucking cool. These are awesome. To kind of illustrate, I couldn't find the best, but this is an old slow-mo guy's video talking about if a bullet can go through a bunch of panes of glass. The important thing is we're going to look at what happens to the actual panes of glass. Imagine these as big sheets of gas, right? And the bullet as a very, very fast clump of plasma or other charged particles, or even just another clump of gas. So as it comes in, this is really cool, by the way. This super slow-mo shot can actually show shockwaves through this glass, which is really, really cool. Like, I'm going to take this frame by frame. Look at that. Look at these shockwaves as they expand out. That's really, really cool. But anyway, that's not the important point. Keep your eyes on this pane of glass over here, and we can talk about what's happening here. So when it goes through, what ends up happening is the shockwave from that pulls all of the rest of it forward. And this is true for a lot of materials, including things like gases. You're basically, almost think of it like a sonic boom in a way. It's pulling that material through and leaving a circular, raised, or indented, depending on the way you're looking at it, pattern in that original material. And that's exactly what we're seeing when we zoom in here. These individual little holes are those kinds of almost impacts. I guess they're not really impacts, but pass-throughs, which is really, really cool. The other two things that this image highlights are both the same, actually, and we're going to look at this bottom one, this number 4 right here. This is a collection of dust or gas somewhere pretty far away from this supernova. I believe this one is actually like a couple hundred light years in the background. I don't remember for sure. It might be this one. Doesn't really matter. These are not part of the original supernova. These are very disparate sources, but they're lighting up in this image too, way more than the rest of the interstellar medium. And the question is, well, why? Why is this unrelated clump of gas or dust lighting up in such a way that it's showing up so like prominently in this image? Like, you've got gas and dust throughout this entire thing. Like, these voids where nothing's happening, it's not like there's nothing there. There's might be less stuff there, but there is stuff there. So why does this stuff show up so bright if it's not part of the original explosion? Well, it turns out that these are showing what's called a light echo. And what a light echo is when the supernova goes off, you have a huge amount of light being produced. Right now, what we're seeing is the residual of that. This is not the original light. This is all of the actual material emitting light. So all of this reddish, purple, pinkish stuff, this is the actual supernova material that came off of the star when it exploded, being bright in itself. This is not actually the light from the original explosion that was created in the original boom. And the same thing with the gunsmoke effect. Like I said before, this is synchrotron radiation. So these are the individual particles moving at around 10% or ish of the speed of light, spinning around in a magnetic field. None of this is the original light from the supernova. These are places where the light from the supernova explosion was absorbed and then later re-emitted by that gas. Similar to how the gas and the plasma from that original explosion is still emitting light, we can have things in front of, behind, or further away from the original explosion catch the light that initially came from that explosion, absorb it as energy, and then re-emit it as heat, or in this case, infrared radiation. So that's what we're seeing here. That's what all these gold sections are, and there's tons of them. They're all over the place. One here, one here, one here, one here. There's some over here. There's some back here. There's some actually in that original pane 1 over here, though this is talking more about the gas here. They're all over the place, and that's what these are. These are light echoes. And the cool thing is that these can tell us a lot about the original explosion itself. They can tell us a little bit about how bright, how luminous that original explosion was. And it can tell us the geometry of the space around. There's a lot of cool stuff that these light echoes can tell us. We're just getting these images in. There's a lot to be looked at here. Let's jump over to this image, back to the mid-infrared image. So if we think about our electromagnetic spectrum, this is lower energy, so this is further in the, I should say, lower energy, higher wavelength. This is closer to visible, so this is closer to things we would see with our eyes, and this is closer to stuff that we would feel with our hands. This is heat, as we would perceive it as humans. So what is all of this reddish-orangish stuff that's going around on this outside that we very clearly do not see in this image? This is another result of the shockwave. Similarly to how these are charged particles in the shockwave that are spinning around magnetic fields, this is the actual gas being pushed together by the shockwave. Everyone here has seen a shockwave before, I'm sure. I actually should have pulled one up. Oh, this one's awesome. I love this one. Look at that. That's so cool. I love that so much. So when you have an explosion like that, you can watch this shockwave, and the reason you can see the shockwave physically is that it is actually disturbing the material. If we think about this as if it was a star or an interstellar medium, right? So we have a star down the tunnel, and all of the stuff in the tunnel is the interstellar medium. As that original explosion causes a pressure wave, it forces all of this stuff together. In this case, it looks a little different because it's more of an expansion than a contraction, but it doesn't really matter. The important point is that it causes all of that stuff to shake and get really clumped together and become energetic, and that energy is then re-released, as this mid-infrared radiation, which we cannot see in this image because it's too cold. This stuff is all a result of motion, so we're talking actual physical motion, compression, friction between the actual things themselves, which is only going to show up in the mid-infrared or colder parts of the spectrum. If they were any hotter, they would show up in here, but they're not. Not like this plasma that's very, very hot. Some of it is actually luminous in the visible. This is all luminous in the mid-infrared. So this is all basically heat. So is this, in fairness, but this one is largely heat. What we would describe as heat, I should say. Humans feeling heat. The last part of this image, which you've probably been looking at and you're like, Xoren, why haven't you talked about this yet? This is obviously the most interesting part of the image. If we look at the near-infrared, the central void, other than that gun-smoky stuff around, is basically completely empty, and that's to be expected. If we have a star that's gone supernova, it has exploded. It's not going to leave much in the center unless it made a white dwarf, which it doesn't look like this one did, or a black hole, which again, it doesn't look like this one did. So what is going on in here that in the mid-infrared we see all of this interesting green stuff? If we look over here, we don't really see much other than the actual plasma, but this is very clearly, like, if we see this structure right here is this structure right here, this green stuff doesn't really line up particularly with any actual plasma in the image. It's kind of separate, and the same goes for over here and down here, and especially in the middle, like I said before. The question is, what is this stuff? And the interesting answer is, we don't really know. All of the sources that I found originally, because again, these images kind of like just dropped, and I think it was actually, it might have been today, December 11th to yesterday. We don't really know what this stuff is. It's an interesting conundrum as to why there is a strong mid-infrared signal just sitting in the middle of this. We're not really sure. I don't even have a really good guess because I don't really know the process that we're looking at here. I haven't done enough research, but this indicates some sort of very strong mid-infrared signal. Something is very hot in the center here, though not extremely hot to the point where it's luminous and visible. Maybe this is some sort of extended radio source that's just putting out enough energy that it can be seen in the higher parts of the spectrum. Maybe. I really don't know. Long story short, we don't know what this is. Right now it's being dubbed the Green Monster, and we really don't know what's up. These images are absolutely gorgeous. If you want to see them, they're up all over the place. NASA has posted them. Basically every single news outlet that covers astronomy and JWST stuff has shown them. They're all over the place. If you can find a higher res image, I very, very highly recommend take a look at them, zoom into these portions that the press releases have pointed out. Very, very cool stuff. This supernova remnant has been observed before. In fact, I actually pulled up the picture, though here it is. This is what that same thing looks like to Hubble. So here's JWST, here's Hubble. A huge difference. Now, mind you, Hubble's still great. You can still see tons of this structure, but look at how much better JWST is. Look at how much more we can see with this new telescope. It's freaking awesome. It's so cool. Like, this is amazing. This is brilliant. I feel like I'm in the meme. This is brilliant, but I love this. So, very, very cool stuff coming out from JWST, as always. Hopefully there's going to be more to talk about, and hopefully we'll have an answer to what sort of this green stuff in the center is sometime soon. Lots to talk about, lots to see.